In this lecture, we'll discuss the implications of the block size and the associativity and how the two are interrelated. Let's start by looking at an example of a real processor cache. So this is the Intel Core Duo. It was codenamed Iona. It has a 32 kilobyte L1 cache that is 8-way set associative and has 256 bits. So if we assume that this processor has a 64-bit address, the question is, what is the address mapping for access to this cache? The address mapping tells me which bits are used for the tag, which bits are used for the index, and which bits are used for the offset for this cache. In order to answer that, we need to answer the following questions. We need to know how many bytes per cache block we have, because that will tell us the number of bits for the offset. We need to know how many sets are there in the cache, because remember, I need as many index bits as I needed to create a unique code or a unique identifier for each set. So I need to know how many sets are in the entire cache so that then I can know how many index bits I have. First, I need to find how many bytes I have per set, and then I can divide the cache capacity, that's the total data that's stored in the cache, by the number of bytes per set. So we are talking about this Intel Core Duo that has 32 kilobytes L1 cache, 8-way set associative, with 256 bits per block and 64-bit address. So this is a block. So the block has 256 bits, which corresponds to 32 bytes. There are 8 bits in each byte, so I just have to divide 256 by 8 to get the number of bytes, so I have 32 bytes. And I have 8 of those blocks in a set, because where I get the 8, the information that I have is that this is an 8-way set associative cache, so there will be 8 blocks or 8 ways in each one of the sets. And so with 8 blocks per set, this is 8 times 32 bytes, I have 256 bytes per set in this cache. So I can now draw the rest of the cache. Let's just adjust my own picture here in the slide, and then we can see the rest of the cache. So I will have a number of sets in this cache. The question is how many sets. So the cache stores 32 kilobytes, which is 2 to the 15 bytes. So to find the number of sets, I need to know that I have 32 bytes per block. That gives me a 5 bits for the offset. And now what I need to know is how many of those sets I have in the cache. Well, I have the total capacity of the cache, the 32 kilobytes, and I have established that are 256 bytes per set, because I have 8 blocks and each block is 32 bytes. So that's why I have the 256. It's not the 256 bits in the block. The block has 32 bytes. It's 8 times 32 is 256. So 32 kilobytes is 32 times 1024. And divide by 256, so 1024 divided by 256 is 4, and then I can multiply 4 by 32, and that tells me that there are 128 sets in the cache. If I wanted to create 128 unique combinations of bits, I will need to have 7 bits, because 2 to the 7 is 128. How do I know that? Remember that I always remember up to 2 to the 5. 2 to the 5 is 32. 2 to the 6 is 64. 2 to the 7 is 128. So I have 7 index bits. So now I know that I have 7 index bits, I have 5 offset bits. How many bits I need for the tag? Well, I get the total size of the address, which is 64 bits. and I subtract those two numbers, and the remaining bits are for the tag. So this cache will have tags of 52 bits, will have index of 7 bits, and will have offsets of 5 bits. So that is the answer for my question. And the way I will decompose this address now will be 5 bits for the offset, 7 bits for the index, and 52 bits for the tag. I do have a vertical lines here. For some reason in the video they do not show because of the resolution of the video. If I want to number my bits now, my bits 0 to 4 will be for the offset, my bits 5 to 11 will be for the index, my bits 12 to 63 will be for the tag. Now, as you've seen, I have examples of caches that have higher associativity than 2. In the previous lecture, we saw how we identify a block, how do we find the least recently used way in a set when we need to do a replacement by maintaining a single bit for the least recently used bit. However, if I have a higher associativity, how could I maintain the least recently used bit for higher associativity, or the least recently used information? I need to know what is the least recently used way in a set in order that I can replace. And of course, I cannot maintain with a single bit if I have an associativity that's higher than 2. So let's look at an example for a 4-way set associative cache. And let's consider that I will try to maintain the least recently used information, and I will need 2 bits per set. So I have my valid bits and I have my least recently used bits. In this representation here, I have 1 set per line. So this will be the way 0, way 1, way 2, and way 3 of one set, and way 0, 1, 2, and 3 of another set. So in this cache, I have only 2 sets, so it's a very small cache, so my index is 1 bit. Just to illustrate how I do the least recently used information. And my assumption here will be if a way in this set has, so each set has 4 ways, way 0, way 1, way 2, and way 3. If a way has the least recently used bits 1, 1, it means that it is the least recently used one. If a way has the least recently used bits 0, 0, it is the most recently used way. So if I wanted to use this scheme to maintain a true least recently used information, what I'm going to do is, if a reference with index 1, for example, that match the way 0 occur, what we're going to have to happen? So I'm doing an access that matches this way here. So this way has to become the most recently used way. So this way has to become the way 0, 0. I'm going to have to change that way 0, 0, but I'm going to have to change the bits of the other ways. So this one that was 0, 1 becomes 1, 0, and this one that was 0, 0 becomes 0, 1. So I add 1 to the counter that I have in front of each one of the ways. And the problem is that incrementing all those counters, so I end up accessing, I was accessing 1 block, and I end up changing the least recently used information for all the other blocks in the set. In hardware, that update of many different counters is very expensive. So we do not maintain least recently used, precise least recently used information when we have a higher associativity. And for a long time, caches would not have much higher associativity because it was difficult to maintain least recently used information. One alternative that we can do to least recently used information is to use a policy that is called the not most recently used policy. So that's an alternative to the true list of recently used information. So what we have now, we group our ways into two groups. We have group 0 and group 1. And we have a single list recently used bit, a single bit that's no longer my list recently used, is my most recently used. So I will always record in which group the way that I use most recently is. So, and what I'm going to do is to ensure that no way that is in the most recently used portion of my set will be replaced. I always will replace from the other group. So I always recording where did I did my most recently access, and I will protect that half of the set, and from the other half I can replace. Then the question is, what will replace from the other half? So this policy did not work very well for quite a while, because there was no good way to select from the other set, because the best way to select from the other set, from the other half, is to select randomly. Because if you do anything that's not random, you can come with worst case situations in which you end up selecting the worst possible way to replace. If you select randomly, then you do very well. And it was a number of years back that some scientists at IBM came up with a way to produce true random numbers in hardware. Producing random values in hardware is actually quite difficult, and it was not nobody knew how to do it until a group of scientists at IBM came up with a way to compute true random numbers in hardware. Once we have those true random numbers in hardware, then you can adopt this policy where you replace from the half of the set that has not been used recently. So you are protecting the most recently used half, and you are selecting from those randomly. There is another alternative that can be used, that is a tree-based algorithm to approximate list recently used. In this example, we'll do an example for a four-way set associative cache. And what we're going to do here, we have these three. So those are the references that we could make. It's very common when we study cache that we simplify everything and we use a single word to represent an entire block in the cache, because all we care when we are talking about replacement policy is where the references have gone in which way the references have gone into the set. So assume that these are four different ways in a set in the cache. And what I'm trying to do is to maintain an approximation to the least recently used information by using only 3 bits. Those are the 3 bits that I have, those circles here, and they will indicate in which way is my most recently used path. So what I'm going to do, I will use dotted lines to represent my most recently used path. And whenever I do an access, for example, if my first access is to B, I'm going to come from the top of the tree, and I will start at B, and I'll make my path to the root as the most recently used path. I have just accessed the way B, and for every bit, I will indicate that the other side is not the most recently used. And that's all I do. So my first reference was to B. Now it's indicating that if I needed to replace something, I start at the root of the tree and I go in the direction that's not the most recently used. So if at this point I need to replace something, I would be replacing either C or D, but not A or B. When I do my next access, that is C, now it's indicating that my most recently used is C, and it's clearly indicating that my not most recently used is A. Notice that at this point, the choice between A and D is arbitrary, but I pointed to one that's not the most recently used. Now, if I access A, I'm gonna change again the tree. Now my most recently used is A. I definitely not replacing that, and I'm gonna be replacing my not most recently used D, and you can see that D is the reference that has not been accessed in a long time, and that's the reference that this approximation algorithm is pointing that I should replace. And finally, if I now have a reference to D, then D becomes the most recently used one, and the algorithm indicates that I should replace B, which is the least recently used one. So this algorithm approximates very well the least recently used policy. It requires n-1 bits per set for an n-way set associative cache, and it performs very well. This algorithm is actually implemented in the L2 cache of the IBM Power 4 processor. And in some years past, implementing this tree-based algorithm was one of the early labs. I believe that was lab 3 in 229. So students would implement this tree-based algorithm for least recently used policies approximations in a lab much before we studied cache in 229, and they would implement that in RISC-V. The next question is, how much associativity do we need to have? So we have been talking about two-way set associative, 8-way set associative, and different ways. So increasing the associativity will decrease the miss rate because now I have more flexibility. And I could go all the way if I make so that any address can go to any place in the cache. I have what's called a fully associative cache. But the problem is that then, when I never have an access, I have to check the tags of all the blocks in the cache. And that can slow me down. So increasing the associativity decreases the miss rate, but with diminishing returns. In a simulation of a system with a 64 kilobyte data cache with 16 word blocks, using the spec 2000 benchmarks, a one-way set associative cache gave a miss rate of 10.3, a two-way gave 8.6, a four-way 8.3, and an eight-way 8.1. This is data cache. Those kind of miss rates are not observed in instruction caches. The instruction caches have much lower miss rates than that. But just to illustrate that there is this curve of diminishing returns. As you increase the associativity, you don't increase your performance as much. And now we'll just look at a different drawing or a different way to look at the cache organization, so that again we can look at the decomposition of the address into the different components. So in this case, each set is lined out this way, and in this illustration here, each set has a single word because I have 2 bits for the offset only. So, each block has a single word. I have 2 bits for the offset only. Each set has 4 ways because I have 4 different blocks where I can have the data with their tags. I have a valid bit for each one of the ways. And so when I do the access, what I will use the 2 lower bits for the offset. I will have the 8 bits because I have 256 sets in this cache, so I have 8 bits for the index, and the remainder 22 bits, I have a 32-bit address, will be used for the tag. Just like before, I'll be comparing the tag in each one of the ways in the set that was selected with the tag that comes from the address. One of them may match. And if that one matches, then I'm going to check whether the valid bit of the one that match is valid. And if the valid bit is valid, then I got a hit. So the one of these hit bits for each one of these groups here will be 1 if it's a hit. And that gives me the hit information for the processor. Notice how I manipulate the data in this case. Remember that in this simple example, I have just 1 word per block. So I take the word for each one of the ways, and I bring them all into this multiplexer. And then I use the hit information to select one of the 4 entries of the multiplexer. So I have these 4 bits coming in here, and they will select whether which one of those 4 entries should be sent as data to the processor. So I will send, for example, if this is the heat, this bit 1 here will come and it will select the correct input, that in this case is this one, to go out into the multiplexer. So that's how my cache works. So one of the question is, what is the storage capacity in this cache? So I can see by the number of bits in the offset that this is a cache that has 4 bytes per block. So it's a single word per block. And I can see that there are 4 blocks per set, and there are 256 sets. So the storage of this cache will be 4 bytes per block times 4 blocks per set times 256 sets per cache. So I have 4096 bytes in the cache, or this is a 4 kilobyte cache. Now, the next question is, how many bits have I used for the storage of the tags only in this cache? Because this gives us a sense of how efficient the cache is to store data, because the tags also have to be stored in the cache. So what's the size of each tag? Each tag is 22 bits. And I have 4-way set associativity, so I have 4 tags per set, and I have 256 sets. So for the 4 kilobyte cache, that was 4096 bytes of data in the cache, I use 2816 bytes for the tags. So you see that more the amount of space used for tags is more than half of the amount of space used for data in the cache. So a significant part of the storage in the cache is used to store the tags. So I'm going to stop this part of the recording here, and in the second half of this lecture, we're going to talk about replacement policies.